So good morning everyone, I am Dr. Neeraj Gupta. Now start with the continuing lecture of signal flow graph. Now in the previous lecture we have discussed about the reduction of a block diagram to a single transfer function. Now we will discuss a technique for reducing the signal flow graph to a single transfer function that relate the output of the system to the input. So we discuss the technique for reducing the signal flow graph in this case. Now in the block diagram reduction technique, it actually requires the successive application of fundamental relationship in order to arrive at the system transfer function. On the other hand, the Mason's rule, that is for reducing the signal flow graph, we use the Mason's rule to a single transfer function, and it requires the application of only one formula. That is, one formula is enough to for the transfer function of the system. Only one formula is required, and for getting the transfer function of the whole of the system. And the formula was derived by S.J. Mason. It was derived by S.J. Mason. This formula was derived by S.J. Mason in 1953 when he related the signal flow graph to the simultaneous equation that can be written from the graph. However, it is complicated to implement the formula without making mistakes. Specifically, the existence of what we later call the non-touching loop increases the complexity of the formula. However, many systems do not have the non-touching loops, which we discussed later on. And for these systems, the Mason's rule is easier to use than the block diagram reduction, where there is there are less non-touching loops. Non-touching loops that we can discuss. Now, Mason's formula has several components that must be evaluated. First, we must be sure that definitions of the components are well understood. Then we must exert care in evaluating the components. To the end, we discuss some of the basic definitions applicable to the signal flow graph, and that we state Mason's rule, and then we can discuss it with some examples. Now the first definition of first definition is the loop gain. So what is the loop gain? Loop gain is basically the product of branch gains found by traversing a path that starts at a node and ends at some other node, and that is the same node, following the direction of the signal flow without passing through any other node more than once. For example, if you see that here are four loop gains, like you see, let us suppose that we have the loop, this one. So we have G2H1. So we have G2H1. Then the second one is second loop is G4H2. This one. Second loop is G4H2. So it is G4H2. And the third loop is G4, G5 and H3. You will see this one, G4, G5 and H3. This is the third loop, that it starts from this point and then ends at that very point. And the last loop is G4, G6 and H3. That is, it starts from here, then moves like that only, and then it moves to that. So G4, G6 and H3. So this is actually the loop gain, which is the product of branch gains found by traversing a path that starts at a node and ends at the same node. Now the second is the forward path gain. So it is actually the product of the gain found by traversing a path from the input node to the output node of the signal flow graph in the direction of the signal flow. Here we have this forward path gain. We have the two forward path. Here we have one forward path, two forward paths. So we have the two forward path gains. One is like that, and second one is like that. So that is, the first is G1, G2, G3, G4, G6 and G7, and second one is G1, G2, G3, G4, G5 and G6. So these are two forward path gains. Now third definition is the non-touching loop. Non-touching loop means that loops that do not have any nodes in common. From this you will see that this loop and all the three loops doesn't have any common node. So in the figure, loop G2H1 does not touch the loops G4H2, this one, G4G5H3, that is this one, and G4G6H3, that is G4G6 and H3, G4G6 and H3, and it is G4G5 and H3. So this G2H1 does not touch that, so it is a non-touching loop in this case. So what is the loop, and next is the non-touching loop gain. So you will see that it is the product of the loop gain from non-touching loop taken 2, 3, 4 or more at a time. Now in this figure you will see that G2H1 and loop gain G4H2 is a non-touching loop taken 2 at a time, and in this case there are 3 non-touching loops taken 2 at a time. That is, we have taken 2 at a time and we have 3 non-touching loops. So here in this case there are 2 non-touching loops, that is, there are no non-touching loop gains taken 3 at a time. That is, 3 non-touching loop doesn't exist in this case, and we have only the 2 non-touching loops. Like let us suppose that we have the gains this G4 G5H3 and G4 G6H3. So this one, G4 G5H3 and G4 G6, so these are not non-touching since the 2 nodes are common. So we have to find that type of the loops which doesn't have any node in common. Like you have the 2 non-touching loops, like you have this one, and all other are not connected to this one. So these come under the category of this 2 non-touching loops. Now we are ready for this to state the Masons gain formula. Now, as per the Masons gain formula, the transfer function of the system represented by the signal flow is given by this Cs by R is equals to sigma is equals to summation of Tk del K divided by del. Now K in this case is the number of forward paths, Tk is the kth forward path, K is the number of forward paths. In this case I think we have how many forward paths that we have already discussed. We have 2 forward paths, and K in this Tk is the kth forward path. That what is the kth forward path is Tk, and delta is equals to 1 minus the loop gains, whatever the loop gain we have. We have I think 4 loops in that, so these 4 loop gains plus 1 minus that is summation of loop gain plus summation of non-touching loop gain taken 2 at a time. So that we have discussed in some time back, that is non-touching loop taken 2 at a time. So there were how many combinations were there taken 2 at a time? There were 3 combinations. Now next is minus summation of non-touching loop taken 3 at a time, so it was 0. No non-touching loop was there which taken 3 at a time, plus non-touching loop taken 4 at a time, it was also 0. So the formula is like that. So delta is given by this. Now in this case one more thing is left, is the delta K. So delta K is this delta, that is this delta minus summation of loop gain terms in delta that touch the kth forward path. That is, whatever the loop gain terms that touch the kth forward path. If that is like that, that is, if the kth forward path is touched by any loop gain, then we can write here in that. So in other words, del K is formed by eliminating the delta from delta those loop gains that touch the kth forward path. So we take the kth forward, eliminate the loop gains of the kth forward path, and then that term can be obtained, that can be explained with this example. Now note that the alternating signs of the components of the delta. So there are the alternating sign like 1 minus summation of loop gain, then 1 plus summation of non-touching loop gain, then minus, and then plus and minus, like that. Now we will discuss it with one example. Now let us consider a system that we have to calculate the transfer function of the system. So first of all, we want to know about the loop gains in this case. So loop 1, 2, then we have this one 3, and then we have this one whole, that is G2 into H1, first one, then G4 into H2, then we have this G7 into H4, and then G2, G3, G4, G5, G6, then we have G7, then we have G8. So we have how many? 4 loop gains in this case. Also in this case you can see that there is only one forward path, that is from this to this there is only one path, and if there is any other path then we can write. So this to this, so there is only one forward path. So forward path gain in this case is written as G1, G2, G3, G4, G5. Now the second point, we have to calculate the combination of non-touching loops, that is 2 non-touching loops. That is, we have to find out the combination of non-touching loops, first taking 2 at a time. Now see from the diagram, you will see if this loop, let us suppose that this loop is 1, this loop is 2, and this loop is 3, and this loop is 4. So 2 at a time if we take, then non-touching loop this into this, it means that we have G2 H1 into G4 H2, that is G2 H1 into G4 H2. Then second one is G2 H1 into G7 H4, that is G2 H1 into G7 H4. Hanji, hanji. And then third one is that G4 H2 and G7 H4, that is 3 non-touching loops. So it is a combination of 2 non-touching loops taken 2 at a time. Now we have to find the non-touching loop taken 3 at a time. Now from this figure we have considered the combination of the tau. Now since these are also non-touching, these 3, so it is the combination of 3 non-touching loops, that is G2 H1 into G4 H2 into G7 H4. So only one combination is left. So the non-touching loop taken 3 at a time, and there is no non-touching loop taken 4 at a time, as observed in this figure. Now first we calculate the delta. Delta is equals to 1 minus summation of loop gain plus summation of non-touching loops taken 2 at a time, then minus non-touching loops taken 3 at a time. So it can be written that is 1 minus summation of loop gain, then minus summation of plus summation of the gains taken 2 at a time, and then minus summation of the gains taken 3 at a time. Also one more point, that in this case the forward path is 1. So in this case, as per the definition, k is equals to 1, that is forward path is equals to 1 in this case. Now we have to calculate the value of del k. In the del k is formed by eliminating from delta those loop gains that touch the kth forward path, that is which loop gain touch the kth forward path, that we can eliminate that. Since this is only the forward path that we have, so we eliminate that, and we are left with this only. So finally our this delta would be 1 minus this one. All other paths which came in the kth forward path, came in the way of the kth forward path, are eliminated, and we remain with this only, that is 1 minus this G7H4. And finally GS is equal to T1 del 1 divided by delta. Since k equal to 1 in this case, we have calculated the value of kth forward path, that is this one, G1, G2, G3, G4, G5, G6, del 1, that we have calculated by eliminating all the loops which are within that forward path, and then delta can be obtained by 1 minus summation of gain of all the forward path plus 2 summation of 1 minus summation of gain of all the forward path, then plus summation of gains having the 2 non-touching loops and minus summation of gains having 3 non-touching loops, and in this way we find the transfer function. So there is only one forward path, so it consists of only one term rather than the sum of terms. So as a result we get the transfer function from this Mason's gain formula. This is how we can apply the Mason's gain formula. Now this is how a single formula can be used to find the transfer function of the system, and that relates the signal flow graph to the simultaneous equation. So from the graph we can write these equations and also find out the transfer function. So this is the case when there are then the system is not so complicated, and generally we are using it in the state space analysis that we will discuss later on. Thank you very much for this lecture.